Hey, good morning, everybody, to the fifth day of this incredible workshop, and it's not even going to be over yet. Tomorrow is another session, so it's wonderful, and it's a great pleasure for me to introduce Sara Negri, who is going to tell us about axioms as rules for intuitionistic logic. Please.
Thank you. Thank you, the organizers, for organizing this event next to all the PhD defenses. And yes, I will present this paper, which is a joint work with Intel Tesi. And how do we move to the next slide?
You can use
With arrows.
that.
Okay, well, let's skip the table of contents.
Yeah.
So let's start with a recap on structural proof theory. Well, I guess most of us already know this background. It was initiated by Gensen's PhD thesis, investigations into logical reasoning, and Gensen's goal was to represent mathematical reasoning patterns. And the key tool for this enterprise is a sequence calculus, which was more appropriate than natural deduction, especially for classical logic. And however, Gensen's sequence calculus is not the last word, because the formalism of sequence calculus has been later refined and improved, in particular with Ketonen, Olga Ketonen. He was a Finnish physician. He was the only student of Gensen, and he wrote the thesis and defended it in 1944. The main result of the thesis was an improvement of Gensen's sequence calculus with the sequence calculus with invertible rules. And in particular, the sequence calculus that gives a direct decision to see classical propositional logic. This was further developed by Kanger, who proved the admissibility of structural rules for full classical logic, not just propositional. Dragalin developed the intuitionistic multi-succeeding sequence calculus, because with Gensen's calculus, the intuitionistic calculus was a single succeedent, and D. Roydikov who devised an intuitionistic single succeeding calculus, a determinating calculus that was later called G4. All of these studies of this more recent development led to the well-known family of G3 sequence calculus that has been developed also in Amsterdam by Anne Roostra, but there are several chapters in this book, Basic Proof Theory. So Gensen's calculi, LK and Li. I write Li because Lj is an error, because it's the wrong transcription of the Sutherland letter for the uppercase I that resembles a J, but it's an I. And they used a list of formulas, and then they had added the structural rules of weakening contraction and exchange. G1 is a calculus which is almost identical to Genzel's calculus, except that rules have a shared context, and they operate on multisets, so exchange is not needed anymore. G2 has also weakening inbuilt, and this is achieved by modifying the initial sequence and making a context. So the letters, the Greek uppercase gamma delta denote multisets of formulas. And finally, G3 is the calculus in which contraction is also admissible, and this is achieved by restricting the initial sequence to atomic principal formulas. Then there is a further calculus that has been added at the beginning of the list, G0, which is a calculus where all the rules have independent context, because in Genzel's calculus, some were independent, some were shared context, and all the rules are directly, so there is creates a good link between natural deduction and sequence calculus. As linked with the natural deduction with general intuition rules, and this is explained in my book, maybe I'll complete it. Well, the language is the usual language of first order logic. The sequence here in this work, multisets of formulas and finite multisets. Then I use the letter uppercase for formulas and the letters ABC formulas and the end of the alphabet for atomic formula. The degree of a formula is the number of connectors and quantifiers. So this is the calculus, the G3 calculus for classical logic. So as I said, in this calculus, the initial sequence are limited to atomic formulas. Then each connective has a left and right rule, and the rules that have two premises have a shared context. And then we want to have a calculus with invertible rules. So the rules that would not be invertible become invertible by repeating the principal formula in the premise, like the left for all would not be invertible, but it becomes invertible if you repeat this formula here, and the same for right existential. And then there is a left function, which is a zero premise rule. These are the structural rules. So left weakening, that are the formula in the context, right weakening, left contraction, and right contraction that duplicate the formulas, and the cut rule. The cut rule is the only rule which is context independent. So these structural rules are not part of the calculus because they are shown admissible. All the rules of the calculus are invertible with a strong form of invertibility, which is hyperservic invertibility. So if the conclusion is derivable with a certain derivation height, also the premise is derivable, and with the same bound on the derivation height. And weakening and contraction are admissible with preservation of height, and cut is admissible. Then, after this prologue on classical logic, we have to talk about intuitionistic logic, which is the topic of this talk. The calculus for intuitionistic logic is a derivation of the calculus for classical logic. And as usual in structural proof theory, we try to create a platform which is as wide as possible, so the fewest possible differences between calculi for different logics. So the modification of the rules for intuitionistic logic is only in these three rules. Left implication is modified by having this implication formula repeated in the antecedent of the left premise. So we didn't have this formula in the classical calculus. And the single succeedent restriction appears only in the right implication and in the right universal premise. So they must be single succeedent to be applied. And these are the only differences. Left implication is invertible, but right implication and right universal are not invertible in these calculus. And the same admissibility results continue to hold, also with proofs which are quite similar. So what about the extension with axioms? So we, as the purpose of structural proof theory was to study mathematical proofs, what do we do with that? So the first problem that one encounters is that cut elimination doesn't hold if you add axioms. So what one obtains is that the result of cut elimination, which is proved by moving all cuts in a derivation up until they come to the axiom. So one could have a calculus that cuts on all the axioms. But this is not cut-free any longer. So another way, and it was a common belief that the axioms space for systems with proper axioms. But if the axioms are converted into rules of inference, cut elimination is maintained. And the first type of axioms that can be converted into rules of inference are axioms of this form. So universal closure of implication from conjunction of atomic formulas to disjunction of atomic formulas. This is converted by removing the universal quantifier, becomes implicit, so we just have the free variables. And then the antecedent part of the formula becomes the antecedent of the conclusion. The succeeding part of the formula appears in the premise, one disjunct for each premise. And since we want to maintain invertibility, the formulas in the conclusion are also repeated in the premises. And with the slogan, I want to say that the content, the logical content of the formula is inherited to the geometry of the sequent calculus rules. And this has been later generalized to geometric and generalized geometric implication, to which I will now come. Geometric implications, so the word geometric comes from category theory, actually not from geometry. They are axioms of this form. So they're kind of conditional existential. So under some assumptions, which are conjunction of atoms, there is a disjunction of existentials. These letters MI stand for conjunction of atomic formulas. And there is one more element with respect to the previous axiom, which is the existential variable. How do we get rid of the existential? Simply, the existential is replaced by a variable condition. The quantified variable becomes a fresh variable in the rule. So the condition is that the variable, which was quantified, does not have to appear free in the conclusion or in any other formula other than the one where it's written. And also for this class of formulas, the class of properties are maintained, and then it can be used to get a simple proof of Barr's theorem, which is a conservativity result for classical intuitionistic theories. And this has also been used to obtain a wide family of calculi for logics, modal logics and non-classical logic, which is based on cryptic semantics, because these kind of axioms are the axioms that are found in the defining frame properties of cryptic semantics. The generalized geometric implications are geometric implications where one repeat inductively the structure of geometric implication. So one can have an arbitrary nesting of quantifiers. Instead of them for all exist, there are many nesting, and the class of generalized geometric implication is defined inductively. The first class is the class of geometric implication, and then assuming that we have defined all the previous classes, the class n+1 is given by axioms of this form, where the antecedent part is always conjunction of atoms, and in the succeeding part, we have disjunction of existentials over geometric implications in the previous class, in GAN. So, okay, for this, one can obtain also kind of Vivenco style characterization. So one can characterize geometric implications in terms, generalized geometric implications in terms of absence of certain connectives in the negative part of the formula. So they are, one can see that these formulas don't have negation, don't have implications nor universal quantifiers in the negative part. And this is actually characterization, because all formulas that don't contain negative occurrences of implication, neither negative occurrences of universal quantifiers, can be transformed constructively in intuitionistic logic to a conjunction of formulas of that form. And then one can do the proof theory, the structural proof theory for this formula, by generalizing the rules to a system of rules. What is a system of rules? A system of rules is a system in the sense, say, of linear algebra, not in the sense of system of rules in logic. The rules cannot be applied in any order. Here, the system of rules has a precise structure. They are so if we have they are defined inductively. So the first step is the geometric rule. The n+1 step is a rule of this form. So what is a rule of this form? It's a bit frightening, but we read it from the bottom. So the axiom of this form, in the bottom we have the existential variables that were declared, that have to be declared, and I've declared them with some equality. There could be some other device to declare those variables. But then the upper part of the derivation contains rules that belong to the previous classes that we have defined inductively. So these parts of the derivation contain rules in GRS Ki, where this each Ki is less or equal than n. In a simple example of so this is a generalized geometric implication that belongs to the class 1, GA1, and this is the axiom of terminal element in order, say. So for all x there exists a y such that if something is greater than y, it's actually equal. And so these are the two parts. So there exists a y, and this is so it contains an atom that talks about y. So I declare it with that atom, and this is the first rule with the variable condition on y. And then we have the second rule, which has to appear on top. So the application of the first rule is licensed only by the fact that it has the rule of the other part. And so this is the other rule, which follows the pattern, because this part of the axiom is a geometric implication, and it follows the pattern of the geometric implication. So this is all nice, but the problem with this approach is that the rules are not local. And a way to localize the rules is achieved by the method of geometrization, which actually works more generally for any first order axiom. So the method of geometrization is something that goes back to Schuler, but here with refinement we obtain a method that it is enough to consider semi-definitional extension. What do we do with an axiom of this form? We take, so this is a next generalized geometric implication. So we take this part and we define this part with a new atom. This is with an atom with a free variable y, so we call it my. And then it has, so the axiom becomes an axiom of this form. And then we take something that corresponds to a semi-definition of my, because the semi-definition is enough. So something that corresponds to my implies this thing, and that can be rewritten in this way. And then when we have these two axioms, we regard my as a new atom. This follows the structure of geometric implication and so geometric rules. So what we have with this method, which is exemplified, this very simple axiom, that any first order axiom can be converted into geometric rules, and then the derivations become local, so they don't have the huge structure of a system of rules. So each step of inference can be checked locally. It doesn't depend on all the rest of the derivation, which is above. The limitation of the method is that when we compute the formula that corresponds to a geometrization of any first order formula, we are allowed to use classical logic. So it could be that the formula that we obtain is not intuitionistically equivalent. And also it uses, so it gives a conservative extension, but it uses an extension of the language, the new defined atomic formulas. So we ask three questions: whether we can apply geometrization in intuitionistic settings, so without going out from intuitionistic logic, whether we can convert intuitionistically the non-geometric axioms into rules, and can we obtain a geometrization type result, so can we localize? And the answer to all these questions is positive. And so we can see that geometrization can be done also intuitionistically, so staying inside the boundaries of intuitionistic logic. If we consider geometrization of generalized geometric implication, and then we, on the basis of this, also gives us some insights to extend the treatment of axioms as rules to axioms that are non-geometric. What are axioms that are non-geometric? They are axioms that violate this restriction of not having implication in the negative part. For example, the field axiom of existence of inverse of non-zero elements, it can be given in a geometric form in this way. So we replace the negation in the antecedent with a disjunction. And this is now a geometric formula, and it can be treated as a rule. However, this is stronger intuitionistically than the other one. We would like to have rules also to treat this other case. And if we apply, say, geometrization blindly, we will get the formula on the right. And so this is the geometrization theorem that I recall. It says that any classical first order theory has a geometric conservative extension. What it means that by extending, we can extend the language, and we obtain an extension which is conservative. So in the older language, we don't have any new results. And there is an extension of the language and also an extension of the theory, because we add the axioms that corresponds to the semi-definitional equivalences. And let's see now this method with an example. So we consider this formula, P implies Q implies R. This is with a simple case of a non-geometric formula. It is classically equivalent to this formula, which is a generalized geometric formula. It's in the class GA1. But it's not intuitionistically equivalent. So this is already an example that shows that we cannot always use geometrization intuitionistically. But to find the equivalent geometric theory, one uses here disjunctive normal form. But if we start, instead of starting with an arbitrary theory, first order theory, if we start with a generalized geometric theory, this has a conservative extension intuitionistically. This is done by suitably extending the language and transforming the systems of rules into rules in the extended language. And this is done in the way that also preserves the proof structure. Let's see this with an example again. Consider this axiom. It is the atomic form of the axiom of Kripke phrase of bounded depth 2. So we take only its atomic instance. And this is in the class GA2, because we have three nestings here. Then P or P implies Q or not Q. So the first is, so the corresponding system of rules is given by these rules. So the rules are now not written as a big tree, but they are written in a consecutive form, but with indexes that indicate how they have to be composed together. So this is the first rule starting from the bottom. This is the second rule, which has to be applied over the second premise of the first rule, and this is suggested by the indices here. And this is the third rule, which is to be applied over the second premise of the rule rho 1, 2. And this is an example of a derivation. This is derivation of this axiom that uses these three rules. And you see, so if you look at this derivation from the bottom, you see that it uses first the first rule, then there are logical steps up to here. Then here we used the second rule, so we have a P in the antecedent and the adds a Q, P and Q in the first premise, adds Q in the first premise, and then logical steps, and we end with an initial sequence also here. And here we go logical steps until we get PQ. And PQ is an instance of the third rule, which is a zero premise rule. And so here we end the derivation. So this is a derivation in the system of rules that correspond to that axiom. How can we geometrize this derivation? So the idea is to replace each rule with a corresponding axiom, and a corresponding axiom is rephrased in terms of a new atomic formula. So here in the we add we add a new atomic formula for the first rule, and then we add another atomic formula for the second rule, which is this no, we have only two atomic P12 and P122 that have these axioms. So the idea is that this one, here we add a formula that corresponds, so this is like having the negation of Q. So we add a formula that here behaves as the negation of Q. This P122 is something that implies the negation of Q and as this a defining axiom. So we add these formulas and we consider then a derivation that with added formulas that can be restructured with this idea in this way. So now the added formulas are written in red with their intended meaning. So we have here a formula that is behaves like the negation of Q added on top, and then we add the other formula, this P12, that is something that implies P implies Q or the negation of Q, and oops. But this propagates from the beginning of the addition with the logical steps, and in the end, by just adding this Q, we obtain the conclusion. So this part, this derivation now has become a purely logical derivation with no added rules. All the derivation is done in logic. So what we have added is something that corresponds to the generalized geometric axioms, and we have localized the derivations in the same way in which the process of geometrization allows to localize to obtain a local system for arbitrary first order theories. So one can show all these, which has been illustrated with an example, formally by defining a translation from systems of rules to their conservative extensions and back. And then one can show that here if then we have that if the derivation as an end sequence, which is in the original language of the theory, then the rules that we added have to respect the order of the system rules, and this guarantees that the translation can also be reversed. Then how do we get beyond? So this was just for generalized theories, but can we somehow emulate what we have done to arbitrary theories? Well, we consider an extension that removes the ban on negative occurrences of implications. We go back to the field axioms, and for this axiom, we propose a rule which is now differently from the other rules that had the same context in the premises and in the conclusion. Now, this rule has a modified context, so it has a context restriction. So the part that contains the atom which is negated in the axiom has an empty succeedent. So this is in red because it's modified with respect to the pattern that we had for geometric rules. And this axiom is part of a wider family of axioms, which we can call nested theories, that have this form. So these nested theories are theories that allow negative implications, negative universal quantifiers, All the letters indicated there are P with the vector on top is list of atoms, so that it is the conjunction of that list of atoms. And sorry, I have two symbols for conjunction for some reason. They are also the and the ampersand is a conjunction, and then we have the letters indicated with R, N, M. They are all conjunction of atomic units. So we can get actually a rule scheme for all this nested theory. And this rule scheme is also something that will generalize what we had in the rule for the field axioms. But since the rules that correspond to this axiom have some context restriction, this will become a general condition on what is on top of these rules. And so we say that a sequent in a derivation is critical if it is a premise of a rule with context restriction, like right implication or right universal, or a premise of an extra logical rule with context restriction. So the nested rules then become this type of rules. Now, consider that compared to the generalized geometric implication, now in this axiom we have only one level of nesting. So this is the complete rule scheme with one level. But here, what we have here, in the conclusion of the rule, we have the list of multi-set of formulas, the formulas that we had in the antecedent of the axiom. Then there are some dots because the axiom has two parts. One part with this part here and the succeeding. And so here we have the part, say, the forbidden part, the part that was forbidden in the geometric axioms, which becomes, they all become premises with empty succeedent. And then there is the usual part, the part of the geometric axiom, which is translated as before. So this part, which is the nested part, has the restriction that this was the antecedent of the antecedent, and then there is some side condition. Then on top, there is the succeedent of the antecedent of the axiom, this and this part here. And the condition is that in that part between the two sequences, there are no critical sequences. So there are no steps that contain the right implication or right universal. So example, again, we consider this axiom. By this method, it is transformed into this rule. And in the dotted part, there are no critical sequence. And one can see that with this rule, we can derive the axiom. However, this is calculus with a global condition, as we had for the general geometric implication. And the next challenge is to transform these rules with the global condition into local rules. And this is done by adding another syntactic component to the derivation, which is the color. And so we added this color, and well, the letter C, you could also not have that C. It's just a mnemonic to remember that that is like the negation of the atom. If we add the color, then we can localize the rules and also localize the star restrictions. The star restriction becomes a local one because we can reformulate the rules that have the context restriction for intuitionistic logic, that is right implication, right universal, by looking at these rules, one could say, well, so they are like the standard rules because we just weaken the antecedent in the conclusion, but one could rather read the rules root first. So if we read the rule root first, this rule says that whatever color formulas I have on the left, they get removed by the rules. And this has the effect that these rules, if there is a sequence with color formulas, the color formulas cannot be repeated in the premises of the rules. They have to be ignored in the following steps. I show now an example to show how it works. So we consider, we show a derivation of underivability of that formula, not Q implies L, in the calculus extended with this axiom. P implies Q implies R. It shouldn't be derivable because that is not a derivable intuitionistic sequence. Let's look at the derivation using the rules that correspond to the formula P implies Q implies R. And we see that when we apply, so here we have logical steps, here we have the first rule, and then logical step, but here we have the rule right implication. The rule right implication was a rule that ignores the colored formulas. So QC is not copied in the premise. If it were copied in the premise, it would be derivable because we could use the other axiom. We could use this one, axiom 1. So indeed, this device of coloring works for localizing a condition on the order of application of rules that otherwise would be a global one. And okay, this is the general form of the rules for nested theories, and given as local rules that now have the color. Instead of being a system of rules where rules need to be applied in a certain order, it is given by two independent rules with this coloring, and these rules have to be used in combination with the newly modified rules of intuitionistic logic that have this condition on the color formulas. So in this way, we obtain a completely satisfactory proof-theoretic treatment of this class of axioms for intuitionistic theories. Why it's fully satisfactory? Because all the structural properties that the basic calculus has are satisfied. Basic calculus, I mean basic calculus for intuitionistic logic. Of course, it's a bit less than classical logic because the rules are hypersided invertible with respect to non-critical premises. They couldn't be invertible with respect to critical premises. Cut rules are admissible. And conclusion, we can apply safely the geometrization method to intuitionistic theories for generalized geometric implication. and they form the largest class for which the method of geometrization works. To go beyond the generalized geometric class, we need a new approach that can be done in two ways, either as system of rules or as localized rules. And to localize the rules, we need this coverage device. Thank you.
Questions or comments? Very interesting. Yes.
Yeah.
In several of your rules, you had a delta in the conclusion. And why didn't you get that for free from weakening? You had a delta on the right-hand side in the conclusion.
Well, yes, you can always add weakening, but the important thing, you don't have delta in the premises of the rules with context restrictions. And weakening is one of the rules that they want to have admissible to have better control on derivations.
So you get weakening from that.
You get weakening is admissible because it's already inbuilt in the initial sequence of the derivation.
Other questions? Yes.
I was wondering whether, I'm not sure whether this makes sense, that like in the classical case, the geometrization result as a nice application is definition of labeled calculus or model logic. And I was wondering whether you can look at something similar for the intuitionistic case, and maybe you could do intuitionistic model logics.
Yes, but yes. So typically for frame properties, the reasoning is classical, isn't it? So that's why I've always been used to use whatever I needed of classical conversion. Even for intuitionistic frames, you can always reason classically. But, well, yes, one could perhaps use this also for
maybe the classical result is very expensive.
Yes, yes. But let's talk.
Yes.
Yes, I mean, you were studying the standard theory, and you were able to capture additional axioms. But then at a certain point, you said, is this the best you can do? Is this a negative result? Is this a theorem, or is this what you think? Can you further, in other words, do you think that this?
No, I said that the method, the previous method of geometrization works because it could introduce some some equivalencies that don't hold intuitionistically, because if one does geometrization by brute force, you use a conjunctive monoform, disjunctive monoform, and you can even so one can improve also the algorithm of geometrization to avoid, because conjunctive monoform and disjunctive monoform destroy the structure of the formula. So if the formula is a generalized geometric implication, one does not apply that, and one can do something better. But if it is not a general, it means that there are nested parts, and then the standard method of geometrization no longer works for intuitionistic logic. It works for classical logic.
Questions or comments?
So this is the paper that Matteo.
I have a question that probably goes to the more philosophical side of the issue. And like, given the usual problems that like proof theoretic semantics has in extending beyond positional logics, do you believe that this method can be promising for extending the framework to generally mathematical theories with first-order axioms?
Well, yes, so you can do so any theory, so you can do the proof theory of any mathematical theory with first order axiom with geometrization classically. And this also show how to extend for the method for intuitionistic theories. Actually, I didn't talk about infinitary theories, but there are several papers, they are not. There is also with Matteo Tesi, and he has also applied this methodology for axioms, model axioms, and then one can treat axioms that are expressed in the infinitary language. So there are like torsion abelian groups, things like that. They can be all formulated with groups. But in fact, also the word geometric theories is a bit here, as I presented them here, I should have said coherent theories, because geometric theory is a misnomer for the finite case, because there should be infinitary disjunction. But they can also be treated. You extend the language within infinitary disjunction, and then by this methodology also, all conservativity results of classical over intuitionistic theories can be proved very smoothly.
Questions? Thank the speaker again.
Yeah, I had something, but I didn't want to. I didn't want to this number at all.
2 minute break.